I was watching an ant colony the other day and something really amazed me. How do they communicate? How do they follow each other so precisely? They don't have leaders, yet they move with discipline, finding the shortest path to food. This led me to explore a fascinating computer simulation that replicates similar behavior. Imagine thousands of tiny agents moving in a digital space. Each one follows as a simple set of rules. It moves forward, senses its surroundings, and turns towards areas with more pheromones. The result? Complex pattern emerge just like in real life ant trails or slime mold growth. Just like in real life ant trails or slime mold growth. Let's break down how this works in code. Each agent has a position and an angle. It moves forward based on a simple trigonometric calculation, converting angle to xy movement. The agent checks for pheromone in front and to the sides. It decides where to move next based on which direction has the highest concentration. If the left side has more pheromones than the front or right, it turns left. If the right side has more, it turns right. This simple rule allows agent to follow pheromone trail just like ants. Now, instead of handling thousands of agents with CPU calculation, we offload the work to the GPU using compute shaders. Each GPU threads update multiple agents at once, significantly boosting performance. This brings us to another fascinating aspect, the slime mold simulation. Unlike ants, slime mold doesn't have individual organisms communicating, but rather a decentralized network of cells that dynamically form connections. The slime simulation works similarly, but instead of following pheromone trail, like ants, the agents explore space in a way that mimic how slime molds finds food. The process involves deposition, decay, and diffusion of virtual nutrients, allowing the simulation to form network-like structure. The key difference in the slime simulation is how pheromone diffuse across the environment. This is done by applying blur effect to the pheromone map, simulating the way real slime mold extend and retract their network. This function spread the pheromone intensity, helping agent move in a way that mimic the dynamic network growth of slime mold. Over time, this creates efficient web-like structure similar to real-life transport network found in nature. Even though each agent follows basic rules, their collective behavior creates something much more complex, just like how ants find efficient paths to food, or how slime mold solve mazes. This simulation is a great example of how emergent behavior arises from simple interactions without any central control. If you want to explore this further, try tweaking the parameters, change the pheromone decay rate, increase the number of agents, or modify the way they sense their surrounding. The possibilities are endless, and it's incredible how a few lines of code can mimic such lifelike behavior. So next time you see ants forming a trail or a slime mold branching out, just remember they are running their own little algorithm. This whole experiment made me wonder, what if we applied these simple rules to other systems? Could we simulate traffic patterns, design better AI, or even understand how neurons communicate in the brain? Maybe these small-scale simulations have much bigger implications than we think.